What kind of questions are out there, Alec, or what should we be thinking about as well before we jump into our problems for today?
Well, somebody just asked, where can we find our practicum grades? And I'm just looking at a couple different sections in gradebook from my course. It looks like they're not in there yet, but I imagine you'll see them in gradebook eventually.
Yep, we need to upload those to gradebook. That's a good reminder there. And so they should just be on D2L. I know that there's been a Piazza post or two about finding the practicum grades. And since it was out of 25 in D2L, right, you're just going to need to double that score. And it will be doubled when we actually enter it into our gradebook system. And so, yeah, that's a good reminder. Thank you for that. Anything else?
Will there be lecture on Friday? We're going to do more review problems then, right?
Yep. We're going to do kind of an open format review. So we'll kind of take any questions. Today is a little bit more of a guided review, right? I have a sampling of problems, and we'll kind of stick to that for the most part, unless there are, we get through them all or there's absolutely no questions on any of them, which is extremely unlikely. But Friday's class will just be an open format review. So you can post questions, I'll pull up web work. I'll try to grab the textbook. I'll have the old exams, stuff like this. And so we can go over any of this. Yeah.
And then where can I get the link for the Google form? You want to show that maybe one more time?
Yep, absolutely. So it's just on the top of this page right here. If you've gone to this, as the PDF from our D2L site, I did make this, link actually clickable and everything. So you can just click on it and it'll take you right over to it. Otherwise, yeah, I understand it'd be a bit annoying, maybe typing all of this in. But yeah, you can just click on that and it'll take you over. So I'm gonna look at this, I'm gonna grab a couple problems that are maybe most popular, and then we'll do those, and then I'll come back and I'll look at it again. So your votes will still certainly count if you haven't had a chance to actually vote on here. So let me go ahead and I'll pull maybe just two problems or so. What are the most popular ones currently? Let me hit refresh on this. And okay, so we're up to 9 right now. And it looks like the most popular ones currently have got to be what? Example 6B is up there. And then why don't we do 6A as well? That one's at 5 votes, and then we'll come back. But right now it's looking like 7B and 12 are next on the docket. So, but we'll do, looks like all of question 6 first, and then I'll come back and I'll double check and see kind of if things have changed or not. So problem 6 is where we're starting. My iPad doesn't like me jumping between apps too much, apparently. Oh, there it is. All right. So problem 6, right here. So I have a couple integration problems. I guess I might as well start with B, and then we can jump to A, since B was a little bit more popular, but we're just trying to integrate the following. And so we have a situation here, the integral of some rational function. So remember, a polynomial over polynomial. And kind of anytime you have an integral problem, right? There was this order of operations to some extent that we went over, in our chapter 7 days, 7.5. We talked about kind of there's a natural thing, you should try to simplify if at all possible. You should try U-substitutions, if it's simple U-substitution. And for a long time, right, chapter 5 and 6, U-substitution was all we knew. That was our, our strongest and really onlyest technique of integration. So you could try things like U-substitution. And then we got into things like trig sub, like partial fractions, things like this. And so kind of, yeah, just need to go down the list more or less. You could think a little bit about U sub. So if you had U is equal to, and quite often the denominator made sense, right? This is kind of the inside function. It's being raised to the negative first power. So you could think about if U is equal to x squared minus 1, then du would be equal to 2x dx. So in fact, if you just had x on the top, right, you notice that the x and the dx could be absorbed with that and life would be grand. And so, but unfortunately, this +2 sort of ruins things. So it turns out U sub isn't going to be a great way to go with this one. However, right, in that kind of list, I talked about partial fractions, and kind of partial fractions should come to mind relatively quickly with this, just because it's a polynomial divided by a polynomial. And so whenever you have one of these rational functions, polynomials divided by polynomials, partial fractions was a good way to go. And so the steps for partial fractions were, step one is that you need to factor your denominator. So in this case, the numerator, it doesn't factor, but even if it did, right, you don't really need to do that. You only need to factor the denominator. So let's go ahead. We have x plus 2, and we can factor this to x minus 1 and x plus 1. And partial fractions said, well, right, maybe there's a way to rewrite this so that, and we have to remember there's like these partial fractions decompositions, and you have to know when to use what rules and all this sort of stuff. But in this case, it's just going to be a divided by x minus 1 plus b divided by x plus 1. And so there's a whole bunch of things, right? So there's all different sort of situations here that you have to kind of go back and review from. This is 7.4 was partial fractions. So the fact that you only need kind of these raised to the first power, x minus 1 raised to the first and x plus 1 raised to the first, is because that these things are raised to the first power here. If you had something that was raised to the second power, right, you'd have to have, the first and the second power. So maybe x minus 1 to the first and x minus 1 to the second power. Things like this. Also, we had these things, irreducible quadratics, right? And when you had an irreducible quadratic, you had to write it with the ax plus b, right? So you had something more complicated on top. So again, there's kind of, this is a good problem, but there's, of course, a lot more to partial fractions. And so we'd like to figure out what are these constants that make this true, that make these equal functions, right? And so, okay, well, maybe let's drop the integral for the time being. Of course, that's going to be the end game, is that we're going to integrate this thing. But let's go ahead and just set up, we want these things to be equal functions. Remember, partial fractions is just getting a common denominator in reverse here, right? So on the left-hand side, we have our common denominator. Now we want to kind of take this apart and see maybe where did it come from. So again, just kind of getting a common denominator in reverse. And so we need to multiply through by this LCD to maybe solve for this. So on the left-hand side, right, I'm going to multiply by my lowest common denominator, my x minus 1 and my x plus 1. And then on the right-hand side, I need to multiply by this LCD, the x minus 1 and the x plus 1. And so when we do this, of course, on the left-hand side, things cancel out quite wonderfully. And of course, the x minus 1s cancel and the x plus 1s cancel. And there we go. We're just left with the numerator. On the right-hand side, well, these things cancel, but right, remember you have to distribute to each piece. So for instance, when you distribute to this term with the a, the x minus 1s cancel, but the x plus 1s don't. So those are kind of left behind. And when you distribute to the term with a b, in this case, the x plus 1s cancel, but the x minus 1s don't. So you get something like this. And now we're going to go ahead. And quite often we rearrange this and we group all the like terms together, right? So I'm going to try to group all the things with x's, and I'm going to try to group all the constants. So for instance, we're going to have ax plus a plus bx minus b once I distribute. And so I'm going to rewrite this as a plus b, and both of these things have an x. And then I'm going to have a minus b, and both of these things are the constants. And we're going to go ahead and write this. Typically, I like to write it 1x plus 2. And remember, if these are supposed to be equal in terms of functions, right? So this is like a line right here. If you want this to be the exact same line, so it's the exact same function, the only way that this is going to work out is if all of the coefficients are the same, right? So you need to have slope 1. So, okay, whatever that thing is, whatever a plus b is, sorry, I kind of started highlighting a lot there. Whatever that a plus b is, right, that slope needs to be 1. And likewise, whatever the constant term is, whatever that y-intercept is, right, a minus b, that has to be 2. So now we get a system of equations here, right? That a plus b has to be equal to 1, and that a minus b has to be equal to 2. So we have 2 equations, 2 unknowns, and we're back in our algebra days. There's lots of great ways to solve a system of equations like this, right? You can use the substitution method. You can use linear combinations. If you really love determinants and your algebra class went into it, there are things called like Kramer's rule, and you can use determinants and all this fun stuff. But in this case, I noticed that maybe linear combinations is nice, right? That I can just add these 2 equations together. And when I add these 2 equations together, right, the a's double up. but the b and the minus b cancel out. And so that's maybe why this is nice. And so I can quickly solve that a has to be 1.5 or 3/2. And then if a is 3/2, right, I can plug this into either one of my starting equations, and I should get the same result. So I'm going to plug it into the first one, 3/2 plus b should be equal to 1. So therefore, if I go ahead and rearrange this, I'm going to get b is equal to what, -1/2. And right, if you wanted to, you could double check, plug it into the second equation, see that you also get -1/2. So now I know what my a is, I know what my b is, to make these equal in terms of functions. And so now I'm going to go ahead and plug these things in. So instead of a, maybe up here I could put 3/2, and instead of b, I could put -1/2. Right, so that's what my a and my b are. And so these constants right there, they're just constants. They're along for the ride. So we're going to have 3/2 is along for the ride. But when I integrate 1 over x minus 1, right, we know this is going to be the natural log, the absolute value of x minus 1. And again, this -1/2 is just along for the ride. It's a constant. And when I integrate x plus 1, we're going to have the natural log of the absolute value of x plus 1. Again, technically there's small U-substitutions going on here, but these are so small that it's also fine. You can just guess and check sort of deal, double check, right? When we take the derivative of these things, we get back to where we started, and therefore this is the correct antiderivative. And so yeah, with this, oops, let me go ahead, make that a little bit larger. This right here would be my final answer. Questions on this?
I do have one here about just where can I find this review sheet. Maybe they joined just a teeny bit late, but could you take just one more second and show that, I guess?
Yes, of course. So let me go ahead. This is under D2L, right? And the videos is where we've been posting kind of all of the stuff for these. And so yeah, this is a good plug anyway. And so if you happen to miss any of the chapter 10 stuff, it's here. And in particular, so you can see for the final exam review, which I just have at the very end, I have the blank notes. And then later today, once we've done the video and everything like this, I'll upload it and I'll post the video here. And then also I'll upload the filled in class notes, right? So I'll update this. And so any of them that we don't go over in today's class, I'll still answer those, just handwriting out the work and everything, and I'll post that as well. And then you can see day 2, so this is going to be the Friday's class there. We just have a video because, again, this is going to be an open review. I don't know which questions you're going to ask. And so, of course, I'll produce a video, and I don't mind posting the class notes, but sometimes this is, all over the place because, I get one web work question, I get one final exam question from this. So I think maybe it's better or more coherent just to use the video there. Okay, yes. Good. Just as an FYI, as this transitions back, right? One possible way that you could have gone with this, and this is so an alternate way, but it doesn't really save any time or anything like this. You could say with this one that, if I had this just as x divided by x squared minus 1, right, that we could use U-substitution for this. So this was kind of going along what we started with for this problem, is that if you just had the x there, you could use U-substitution, and maybe that's somehow tempting or nice to do this. So you could decide, no, I'm going to split up this fraction then, right? So I'm going to do this with 2 over here, and then x squared minus 1 here, dx. And so you could integrate this one with U-sub. That would be perfectly fine and everything. And then for this one, you would still have to use partial fractions, sadly. And that's why you don't really save anything by doing this. Your partial fractions would, of course, yield slightly different answers, but when accounted for with this U-sub and everything, right, they would be the same overall answer. It'd probably look a little bit different, right? There's lots of properties with natural logs and things like this. So it won't look the exact same, but it will be equivalent, right? If you graph them both, you would see that they graph the same curve. So this is another possibility on how to solve this problem. Good. Any other questions out there, Alec, or things that I'm missing or that you'd like to add?
Just on that last little note that you just made there, it's possible when you said when you graph that, I don't know how it would come out, I'd have to do it, but it's possible that when you see the graphs, they would be the exact same shape, but one might be shifted up or down, and that could just be, because it might be a different C. You have that plus C there. When you do the other version, it could be a different constant. So it could be like a vertical translation of the graph.
Yep, it's a good point. Okay, so with that, we'll do 6A, and then I'll go back to the Google form and I'll check and I'll see if there's been any updates, if there are new popular winners of things that we should be going over, or if we'll just continue and do what we were planning. So notice that this one is very, very similar to B. The only thing that I've altered here is that instead of the x squared minus 1 on bottom, I've changed it to x squared plus 1, right? And now, so when we go through the same sort of process and we think about U-substitution and, you know, kind of this whole storyline of how we integrate a problem like this, right? Partial fraction somehow becomes less tempting, right? Because when you try to use partial fractions on this, right, the first step is to factor the denominator. But x squared plus 1 can't be factored, right? It's an irreducible quadratic. And so there's no way to factor this, at least not over the reals. And luckily, we're not doing complex calculus, right? So we're just sticking to real calculus. Complex calculus does exist. You have to go to math 425, though, for it. So it's a bit later down the road. So, OK, that's not working for us. And so we get kind of stumped. We say, well, what can we do in order to evaluate this? And actually, going back to kind of what we talked about here at the very, very end is useful, right? We can kind of decide to break up this fraction, right? We say we're stuck, we don't know what to do. Maybe we can just separate this thing. And so that ends up being fruitful here. So let me go ahead. I'm going to rewrite this as x divided by x squared plus 1 plus 2 divided by x squared plus 1. And we're integrating that with respect to x. So again, this bit right here, we can use a u sub for. So let's go ahead. Maybe u is equal to the denominator, this x squared plus 1. So du is going to be equal to 2x dx. And we can go ahead and solve. So this is going to be 1 over 2x du. And so let's go ahead and maybe insert this in. So let's see. My x squared plus 1 for this bit is going to become u. And then we have this x. And we're trading in that dx for 1 over 2x du. So we get something like this, and we can see that these x's nicely cancel. So let me just kind of break up this integral. That's how we're going to do this first one. Now, the second integral we're going to have to think about for a second. So let me leave this. We're not going to use the same u substitution here. So I'm going to break this up and leave this one in terms of x's for the time being. This first one, though, right, this 1/2, that's along for the ride. And then I get the integral of 1 over u. So that's going to be the natural log of the absolute value of u. And remember, my u is x squared plus 1. So far things are going pretty good for that. Now we have to think back, how do I integrate 2 over x squared plus 1? So I'd like to throw that out to you guys here. Please type in the chat or the Q&A or something like this, right? How would you integrate 2 over x squared plus 1? And the hint is there isn't a natural log. There's no natural log in the integral here. Yeah, I see it a few times here. It's going to be arctangent. So again, this is the power of having your formula sheet, or maybe you've just done these, so many times that it's now bread and butter sort of deal. But certainly on the final exam, right, you should have printed out next to you the final exam formula sheet. And then if you get stuck on something like this, how do I integrate a particular function? At least skim over, right, and you'll see that arctangent is the answer to this. So we have this 2 that's kind of along for the ride. And then I think the formula sheet quite literally just says, the integral of 1 over x squared plus 1 is arctangent, or tangent inverse, of x, plus some constant of integration. So this one right here, even though it looks so incredibly similar to 6b, right, the techniques that we use are considerably different, right? We don't use partial fractions here. We need to use U-substitution and our chapter 6 knowledge, right? That the integral of this 1 over x squared plus 1 is arctangent. And so again, kind of problems can look quite similar to one another, but you do really have to take your time with these things, go through them carefully, and see kind of what techniques do we need to use in order to solve these. Okay, with that, I don't think I have anything else to say about 6a. Anything that you'd like to add, Alec, or any questions out there?
The only thing I would maybe just add is you might be looking at the formula sheet and saying, oh, that isn't quite on there. Well, it's written in the other order, right?
Oh.
It's written as a derivative. So on the formula sheet, it says the derivative of tangent inverse is 1 over 1 plus x squared. So that's, you know, you should be used to reading those inverse trig functions forward and backward.
Good. So yes, of course, taking the derivative of arctangent, right, being 1 over this 1 plus x squared, that just means it's the antiderivative of 1 over 1 plus x squared. So absolutely. Okay, good. Why don't we go ahead, and I want to flip over here again, go to this form, see if we have any more responses, assuming that my internet holds up and all this sort of stuff. Okay, we're at 11 now, good. And it looks like 7A and 12 are tied right now at 6 votes apiece. So, or no, 7B, sorry. 7B and 12. So that's what we'll do next. And then we'll jump back here and see who's in the lead. So 7B and 12 are next. So for 7, we just have evaluate the following. And we have this thing here. So it's a derivative, right? 1 plus 2x raised to the 3x power. We want to take the derivative. We want to evaluate this thing. And then let me just, I may do this entire problem, and then I may forget that 12 is next. So I'd like to go down here. I'm just going to star this, just so I don't accidentally forget. Okay, so let's go ahead and take the derivative of this thing here. Now remember, well, I guess starting back in Math 132, we've dealt with things like if I wanted to take the derivative of 1 plus 2x, you know, raised to the 3rd power. This was something that we did back in Math 132. And for this, we just need to use, well, the chain rule and the power rule, right? Bring the 3 down, all that sort of stuff. So in this case, this is just like a more complicated version of something like x to the n. And then we've also done, in Math 133, we learned how to take derivatives of exponentials, right? Things where the variable is in the exponent slot. So something like if I wanted to do 2 raised to the 3x, right? So in Math 133, we dealt with that. In general, it looks like, you know, a to the x sort of deal. And we know now the derivative of these sorts of things. But unfortunately, both of these fail when you have the variable that is both in the kind of base there and in the exponent slot, right? So kind of there's some hypotheses for these formulas, right, that we have here in Math 132 and 133 that are sometimes overlooked. And they say, for instance, that this n needs to be constant. If it's not a constant, then the formula doesn't work. And likewise, this a right here, in order for the formula for the derivative of a to the x to work, it needs to be constant. A needs to be constant. And so the fact that you have both the base, your 1 plus 2x is changing with x, and your exponent, that 3x, is changing with x. Sadly, neither of these work. So we came up with another technique back in our 6.4 days when we were doing problems like this. Was it 6.4? Yeah, 6.4 sounds right. And can anyone remind me, what is the technique in order to solve this sort of problem? What do we need to do? Yep, and I see it here, logs. So we need to apply a logarithm. So notice this problem does not say use logarithmic differentiation. It just says, hey, take the derivative, right? And you have to decide when to apply logarithmic differentiation. And this is exactly when, right? When you have a variable in both the base and the exponent, none of our other techniques work. The only way forward is with logarithmic differentiation. And so yes, we need to apply a log. So let's go ahead. I'm going to back up for a second. I'm just going to go ahead and rewrite this function, and then we'll take the derivative of it. So I'm going to rewrite it. You know, you can use f of x, you can use y, anything like this. And then, as suggested, we're going to apply a logarithm. And the reason why we're going to apply a logarithm is because they have some wonderful properties. We don't really care about it being a logarithm particularly, other than we want to use its great properties. And one of the properties of the logarithm says that you can take exponents like this, 3x here, and you can move them down in front. This is called the power rule for logarithms. There's a lot of different power rules, right? We have power rules for derivatives, power rules for antiderivatives, power rules for logarithms, right? So yes, we need to use the power rule for logarithms here. Take that exponent, move it down. Notice I haven't taken a derivative or anything like this yet, right? So the next step here, well, we're interested in solving for the derivative of our function here. So my end game is that I would love to have y prime equals, right? If I can figure out the derivative of that function, the y prime, then that's how we win. And so, okay, the logarithm, it's great and everything. We get to use its property. And now notice you don't have a variable in both the base and the exponent. They're all in the bases now. And so that's what we were looking for. Now we can apply some of our earlier rules. But notice that when you take the derivative of the left-hand side, you have kind of ruined things a little bit, right? You don't just get y prime, unfortunately, because the derivative of the natural log is 1 over. So you have to do 1 over, leave the inside alone, and then multiply by the derivative of the inside. And the derivative of y with respect to x, well, usually we just notate this as y prime. On the right-hand side, well, we see that there's a product, right? So we have to use the product rule. So it's gonna go the derivative of the first times the second plus the first times the derivative of the second. And don't forget your chain rule, right? So also take the derivative of the inside. Derivative of 1 plus 2x is going to be 2. And so, okay, I could go ahead and maybe simplify this a little bit here. So let me write 3 natural log of 1 plus 2x. Let's see, in the numerator slot, we have a 3, an x, and a 2. So I can write 6x altogether. And in the denominator, all we have is this 1 plus 2x. And in order to solve for y prime, we just need to bring that y to the other side. So we're going to bring that y to the other side. But of course, whenever possible, right, we like to write things in terms of only x's, right? So if we don't have to bring in the multivariable case, let's not. And so instead of y here, I'm going to write my original function. So get this all in terms of x's. That's what we started with. Y was something we created technically here, right? The problem didn't have anything called y. So let's go ahead and get it back in terms of just the variables that the problem specified. So this right here would be my final answer. And again, logarithmic differentiation was absolutely necessary here. None of our other methods can solve this style of problem. Okay. Questions or things that I'm missing or, yeah. I guess some people would argue at least that what you could do this in another kind of clever method that you don't exactly use logarithmic differentiation, but you kind of use these inverses, right? You would rewrite this instead of, some expression a, you could write this as e to the natural log of a. And so still you're applying a logarithm. You get a logarithm here and you're going to use its properties. But maybe you could get away without, doing something exactly called logarithmic differentiation. Good. Any other questions, comments, things I'm missing, Alec?
Nope, I don't think so. That last little comment, I was about to throw that out there, but you got it. Somebody asked that question, and so you just answered it. So yeah, that's fine too. Just rewrite it as e to the natural log of that, and you do all the exact same stuff pretty much. Yep. And works out the same way.
Okay, awesome. Well, that's what 5B here. Let's go ahead and, 7B. And let's go ahead and move on to example 12 as promised. Find the limit of the sequence, the nth root of n squared. So the limit of the sequence here. And so yes, remember whenever it says the limit of the sequence, right? There's only really one natural limit for sequences to have. And that is, right, this is some code phrase here that means take the limit as n goes to infinity of our a sub n. So in this case, the nth root of n squared. right? And so the question is, well, what does this approach? Does it actually approach anything, or does it go off to infinity or negative infinity, or does it just oscillate, right? So does this converge or diverge? We can see one of the possible answers is just that it diverges, and then we have that it converges to a few other things. And so that's really, again, this is kind of some code phrase. You need to know that this is the same as, taking the limit as n goes to infinity of the sequence. Because again, remember, sequences are really just lists of numbers. So the question that we're asking is, long term, what happens to this list of numbers? Does it seem to get close to something or not really? Okay, well, the first thing that you could do anytime that you have a limit, right, is that you try to plug in infinity everywhere you see an n, right, in your variable here. So we could say, okay, well, this is going to be the infinite root of infinity squared, right? So this is what it's getting close to. And all of a sudden we see, oh, this is a bit of a pain here. We haven't really dealt with infinite roots or things like this. And so maybe it's a good idea to go ahead and rewrite this, and then we can try again. So let me go ahead. Remember, whenever you're taking a root, you could instead rewrite this as an exponent, right? So you can write this as n squared, and then we write it raised to the 1 over nth power. So that's the same, right? Like the square root is the same thing as the 1/2 power, cube root 1/3, so on and so forth. And then we notice, well, it's pretty tempting, right? We have powers raised to more powers. Whenever you have powers raised to more powers, you can simplify even farther here. And you can make this maybe n raised to the 2 over n, right? They multiply together there. And so as n goes to infinity, right, we're going to have infinity raised to the 2 divided by a very, very large number. And when you take 2 and you divide it by a very, very large number, right, something like 1,000,000, 1,000,000,000, 1,000,000,000,000, right, that's going to be going towards 0. So this is going to be infinity to the 0th power, and this is an indeterminate form. Indeterminate form. And so I guess, first of all, right, of course, if it wasn't an indeterminate form, it was something that we could determine, there'd be no reason why you have to use L'Hopital's rule, right? So for instance, if you had something in some alternate universe, right, if you had infinity raised to the infinity power, that's not indeterminate, right? So if you take a very large number and you raise it to a very large power, right, 1,000,000 raised to the 1,000,000th power, or 1,000,000,000 raised to the 1,000,000th power, well, that's just going to go towards infinity, right? It's just very, very large. But here there's kind of some contradictory things, right? All of these very high roots are trying to slow this thing down, but the thing that you're putting in these big roots, right, is getting very large. And so the question is, what wins out? The things that you're putting into this large root, or the fact that you're taking bigger and bigger roots, right? Because that's certainly slowing things down there. And so that's what makes it an indeterminate. And so this is why we're going to use L'Hopital's rule. So again, we're going to try to use L'Hopital's rule in order to evaluate out this limit right here, which we found was equivalent to what we started with. And so there's a couple different ways that you can view these sorts of problems. What I've done typically in my class is that I say I'd like to consider temporarily an alternate problem. So I'm going to go ahead and just say consider this alternate problem. And my problem, the thing that I'd like to change is that I'd like to impose a natural log. So I'm going to temporarily give this thing a natural log. So again, I'm not solving the exact same problem as I'm tasked with solving up here. I'm imposing a natural log, and of course, later on, we're going to have to pay for that. But for the time being, let's try to solve this problem. And again, it's funny that actually these came right after each other, right? So we just did logarithmic differentiation. And here we're also throwing in this extra logarithm. The problem is, right, we don't have an equality, right? We don't have this like equal to y or anything like this. And so I don't have, a way to apply a logarithm to both sides of things. And so that's why we're going to use this kind of these inverse properties here. I'm going to temporarily give this a logarithm, and then I'm going to pay for this later on. So yes, I'm giving this a logarithm for the time being because, again, we see we have a variable in both the base and in the exponent. And whenever you have a variable in both the base and the exponent, a logarithm is going to be wonderful because of the power rule. So I'm going to go ahead and apply the power rule here for logarithms and make this 2 divided by n times the natural log of n, right? So I'm just taking the exponent and I'm moving it down. And now, right, I told you we're going to use L'Hopital's rule. And of course, right, L'Hopital's rule doesn't work for things like this. L'Hopital's rule works when you have fractions. And so I'm very excited to see that I now have a fraction. If we wanted to, we could even rewrite this. So the limit as n goes to infinity, and we could make this 2 times the natural log of n divided by n. So it works with fractions, and remember it has to be one of two forms, either the infinity over infinity form or the 0 over 0 form, right? Those indeterminate forms is what L'Hopital's rule handles very well. Remember that it doesn't have to be positive infinity, it can be positive or negative infinity, so you can make that switch here. But as n goes to infinity, well, the natural log goes to infinity, albeit kind of slowly, and certainly n will go to infinity. And so we're in this infinity over infinity sort of situation. And this is exactly what L'Hopital's rule handles well. So whenever I'm doing one of these problems and I'm applying L'Hopital's rule, right, I always state exactly where we use L'Hopital's rule. So you should do the same, right? Write a little LH or something like this above the equal sign where you actually apply L'Hopital's rule. There's lots of exams and stuff that I've seen in the past where they say, justify why can you use L'Hopital's rule, and then explicitly state, you know, if you lose L'Hopital's rule, where do you use it? So this infinity over infinity is telling me that I can use L'Hopital's rule, and then here I'm stating with the LH that I'm using it now. So with L'Hopital's rule, we need to take the derivative of the top and the bottom. Well, the derivative of the bottom is easy. The derivative of n is just 1. And the derivative of the top, well, derivative of natural log is going to be 1 over n. And so now we can see that as n goes off to infinity, right? Well, 1, who cares, right? 1's just 1. But we're going to be dividing by larger and larger things, right? Because we have this 2 divided by n. And so this is going to go down to 0. So the limit as n approaches infinity, this will actually be 0 in this case. So notice this one's a little bit cruel here. If you're going too fast, you say, the answer is 0, done. But remember, I changed the problem, right? So I imposed this natural log, right? The original problem did not have a natural log. And so if I'd like to temporarily give this a natural log, of course, I must also kind of backtrack this, right? I have to imply the inverse. Otherwise, right, I'm fundamentally changing things. So since my answer to this problem is 0, I can confidently say that the answer to the original problem, the limit as n goes to infinity of n to the 2 over n, well, the way that you undo a natural log and get back to where we started is by applying an e. So in this case, it's going to be e to the, and whatever answer we had here. So in this case, we had 0, and so it's going to be e to the 0. If you had gotten 1 here, it'd be e to the first power, right? Or e to the second if you got 2, whatever it is, right? And so that you just use this in order to cancel out this natural log. And so e to the 0 power is going to be 1. And so the final answer here is 1. So like I said, this is one way that you can go about doing these things. Another one is you could quite literally just apply both the e and the natural log at the same time, right? And then you're not really doing a different problem. But I find that then you're carrying these things around and you're doing all of these operations in the exponent slot. And so kind of it gets a little bit messy. But that's another possibility as well. How do you usually do these, Alec?
I usually do write it as e to the natural log of, I just usually write that first, and then it's more writing, admittedly, so I have to put the e in front every time. Then I pass the limit inside the e to the x function, essentially. And
that's a good habit to get into anyway, with those continuous functions, the fact that you can push limits inside of continuous functions.
Right.
We find that we need that with square roots and things like this quite often.
Yep, but it is definitely more writing.
Yep. Yep, it's kind of one of these things that you have to, I don't know, not pick your poison, but pick your battle or something like this, right? There's going to be, there's definitely advantages and disadvantages to using either one of these. There's not kind of a unique, correct way. So by all means, yeah, if you like some other method of solving this problem, you guys can use that, certainly. Good, any questions out there about this problem or things so far? Okay, why don't we go ahead and I'll hit refresh here. Let's see, we're up to 14 responses now. Let's see, we just did example 12. So we're good with that. We did 7B, we did all the 6s. And so let's see, I think the next thing, there's a bunch of them that have 5 votes. So 7A has 5 votes. and example 11 has 5 votes. So why don't we do 7A and 11, and then I'll come back and I'll look at this again. So 7A and 11 is what we're doing next. So I'll star this one so I don't forget it. And 7A, okay, evaluate the following. So the limit as x goes to infinity of this thing here, e to the 3x over x squared plus x plus 1. And so, okay, well, we could just try, right? Anytime we have a limit like this, you can see what happens if you go ahead and just try to plug in, I guess, infinity everywhere we see an x. So we'd have e to the, well, 3 times a very large number is going to be very large, so e to the infinity. And then you're going to have infinity squared plus infinity plus 1. So a very large number, you square it, you add another large number, and then you add 1. So this is going to be going towards infinity, the denominator. And when you take e and you raise it to a very, very large power, this is going to be going to infinity as well. So we're in one of these infinity over infinity scenarios, and that's exactly what L'Hopital's rule handles well. So we're going to go ahead and apply L'Hopital's rule to this. And in fact, we're already in this good setup. So this is actually maybe a little bit nicer than the last one that we just did, because we need to do a little bit of work to get it in its fraction form. But here it's already set up in its fraction form. So we can just go right ahead and we can apply L'Hopital's rule. Right? So, okay, we apply L'Hopital's rule. We need to take the derivative of the top and the derivative of the bottom. Yeah, I almost wrote n there. So, okay, the derivative of the top. Well, the derivative of e is itself. So that's some chapter 6 knowledge. Don't forget the chain rule though. So multiply by the derivative of the inside. And then the derivative of the bottom, right, we're gonna have 2x plus 1. And so, okay, we could say, now can we plug in infinity? And when you do this, you see that yet again, you'll get infinity divided by infinity. And so whenever this happens, right, you kind of have to pause and say, am I going in the right direction, right? Certainly we could apply L'Hopital's rule again, but the question is, will it be fruitful? Are we expecting anything better to happen than what we just did, right? There's sometimes with these square roots, right, where you kind of get into this infinite repeating pattern where kind of these square roots are just kind of dancing between the numerator and the denominator, and nothing really ever gets any better. So that's a good indicator that you need to pause and try to do something else, like with an algebra trick or things like this. On the other hand, in this case, I think that we're actually headed in the right direction, because I saw that this was a quadratic, and now it becomes a linear thing. And if I take one more derivative of this, it's just going to be 2. And that's going to break the pattern, right? 2 is not the same thing as infinity. And so I have a lot of hope here that maybe applying L'Hopital's rule one more time will actually get us some result. And so let's go ahead and apply L'Hopital's rule one more time. Again, on the bottom, we just get 2. And in the top, we get e to the 3x. We have this 3 that's along for the ride. And don't forget, chain rule, we need to have another 3 here. And so now as x goes to infinity, right? Well, again, the numerator is going to be going off to infinity, and the denominator is just 2. And so you're going to get a very, very large number divided by 2, still very, very large. So this is going to be equal to infinity. Or we could say, right, that it diverges towards infinity in the case of like sequences and things like this. So yep, this one diverges towards infinity. Questions, comments, concerns? Okay, why don't we go ahead and move on to 11 then? All right, all right, so at t equals 0 hours, we have some bacteria culture. It contains 100 cells. It grows at a rate proportional to its size. Yeah. At t equals 1 hours, we have 200 cells. And we want to know, when will the bacteria have 300 cells? And so, okay, the big thing here, this is a 6.5 question. And in 6.5, we got this code phrase right here. This code phrase just means that this is going to be an exponential function, right? So we talked about in the 6.5 videos and everything like this phrase right here means that its growth rate, so how its population is changing with time, its derivative right here, is proportional to its size. So some constant of proportionality here, this k, times the size of the population, that's p. And when you solve this differential equation, right, so this is a separable differential equation, you end up finding that this is exactly what it requires for this to be an exponential equation. So we're going to find that the population is given by some exponential equation. So we have, maybe e to the kt, and we have some initial population here. So that you can, label with p sub 0, so the population at time 0. I know there's other ways that you can label these things. So if you want to use amounts, sometimes I see these with a's rather than p's. But yeah, so something like this. Okay, we need to know to use this equation, right? Nowhere in here does it say exponential equation. It says it grows at a rate proportional to its size. That's the code phrase that you need to know. Exponential equation. Okay, we know that at time 0 we have 100 cells, right? So this indicates to us, this piece of information says that this is 100. Its population at time 0 is 100. And of course, so you can just plug this in, or if you'd like to double check, right, you could quite literally plug in 0 everywhere you see a t, right, and see that this bit has to be the 100. We also know that 1 hour later, we have 200 cells. So let's go ahead and plug in this information and see what it gets us. So the population 1 hour later is going to be 200. So everywhere I see a p, the population, I plug in 200. And everywhere I see a t, I plug in 1, right? So 1 hour later, we get 200. So this is going to help us solve for k, right? What is our growth rate here? So we could go ahead and divide by 100. Of course, k times 1 is just going to be k. And then we could go ahead and apply a natural log on both sides. And this is going to help us solve for this k, right? So we apply that natural log because it perfectly cancels with the e. And so then we get to k is equal to the natural log of 2. So okay, so far we have now kind of the explicit formula that p is equal to 100, and we have e to the natural log of 2 times t. So we now know what the formula exactly is. We now know the k value as well. And so we want to use this to answer the question, and it says, when will the bacteria have 300 cells? So notice, in order to solve this, we need a when, that's going to be a time value, and we're given the information that the when that we want is when we have 300 cells. So that's going to be a population value. So we have a population value, 300, and we want to know the when. We want to know the time value when this occurs. So we can go ahead and divide by 100. And we get something like this. Again, if we're trying to find when, we want that t. So let's go ahead and apply a natural log to cancel that e there. So we're going to have the natural log of 3 is equal to the natural log of 2 times t, because again, the natural log cancels with that e. And so finally, we're going to have t is equal to the natural log of 3 divided by the natural log of 2. Right? I just need to undo that multiplication, and the way you undo multiplication is with division. So that's why I divide there. And so this right here seems like a good answer. Let's check and make sure it's there. And yes, right here we have the natural log of 3 divided by the natural log of 2 hours. But notice you can see that you have to be kind of quite careful with your work and everything. There's, for instance, you'd be tempted maybe to say C, and just kind of factor out this natural log to some extent. But remember, that doesn't work for natural logs. You can't do that. There's a different rule for quotients for natural logs, but that's not what the quotient rule says for natural logs. So you can't use that. So yep, the correct answer and the only correct answer is D. Questions, comments, concerns, things you'd like to add, Alec?
I guess I would just add, on a problem like this is always a good opportunity too, to just take a second and ask yourself if that answer seems to make sense. If you look at the original problem, right, you're starting with 100, and then in 1 hour it increases to 200, right? So after 2 hours, then you would have 400. So you know that this answer for sure has to be less than 2 hours. Yep. And you know that it can't be negative, which some of those answers up there are, and
yep.
And so it doesn't take too long to realize that that answer seems pretty reasonable.
Yeah, you can definitely, with any multiple choice question, certainly it's quite reasonable to try to eliminate unreasonable answers. So just like Alex said, you can eliminate A, because after 2 hours you'd actually have 400 cells, right, at this proportional growth rate. This one right here, this is going to be smaller than the natural log of e, which is 1, right? So this 3/2 is 1.5. That's smaller than 2.7 and change. So that's unreasonable. And e is negative because you're plugging in a value less than 1 into the natural log. So you can rule that one out. So you can get down to a 50-50 shot just by being clever and knowing, you know, a decent amount about logarithms before you even get into the correct way. So anytime you can whittle down answers, by all means, play the game, right? You need to whittle out any unreasonable ones. Good. And sorry, go ahead.
Oh, I was just, no, you finish first because there's a new question.
I'm happy to move on. Yeah, I was just going to say, is there anything else?
Yeah, somebody just asked, would the rule for log say that the answer is also natural log of 3 minus 2? No, that's not how that works. That would be, if the answer C was correct, which it isn't, but if you look at that natural log of 3 divided by 2, that would be the same as the natural log of 3 minus the natural log of 2, not in parentheses like that. But that's not what the correct answer is anyway.
So yeah, this is what the quotient rule for logarithms says. So that you can have a quotient inside of a logarithm is the same thing as subtracting outside of the logarithm. So the natural log of m minus n. Notice that that's not exactly what we have over here. There is another kind of clever way that you can rewrite this. And in fact, if you choose a different base rather than, you know, e's and natural logs, it comes about a little bit more naturally here as well. But we do have a rule that says what it goes, log base b of a, for instance, is the same thing as the natural log of a divided by the natural log of b. So this was the change of base property. And there's nothing special about the natural log here. You can actually do it for other bases, log base 10 or whatever your favorite one would be here. And so another equivalent way to write this, and so I guess they could be mean and have written it in this way, you could say that this is the same thing as the log base 2 of 3, using this change of base property, essentially just in reverse here. But it looks a little bit cleaner, right, just because you have 1 log rather than 2 logs. But you do have to change the base. So yeah, log base 2 of 3 is the other equivalent correct answer for this. Good. So why don't we go ahead? Probably have time for one more problem here. I'm going to look here one last time, hit refresh. And see. All right, we did all the 6s here. I think we did all of the 7s. Looks like example 13 is next on the docket. Example 13. This one is a work problem. A particle is located at a distance x feet from the origin. We have a force of 6x pounds acting on it. How much work is done moving the particle from x equals 1 feet to x equals 3 feet? So this one is relatively nice. I mean, I know it's been a long time since we've done any of these work problems, and so this is a good review. But remember, the only piece of information really that we have on our formula sheet about work is that work is equal to the integral of the force function. And so here I'm using my variable x, but sometimes we've certainly seen problems with work where it makes more sense to use y. For instance, if you're lifting some rope or some elevator or things like this. Also some of those pumping problems, right? So when you're pumping liquid out, maybe the more natural variable is y. But in this case, I see a lot of x's. And so I'm happy with it. But just know that you can extend this, you can alter this work formula from your formula sheet here by using y's rather than x's. So okay, it says right here quite explicitly, the force is 6x. So we need to integrate 6x. It says we need to figure out the work done by moving it from x equals 1 feet to x equals 3 feet. So, okay, this is specifying what my bounds should be, 1 and 3. And so again, kind of the complicated thing here is the setup, right? Of course, we can certainly integrate this right? But just knowing what to do with this, right? What actions do we actually need to take in order to solve this is the complicated bit. So now that we have this, we can just integrate or find the antiderivative. We can plug in 3, we can plug in 1, and let's see, we're gonna get 3 times 9 minus 3 times 1, and so we get 27 minus 3 is going to be 24. Notice that we have units of pounds and feet. And so foot-pounds is going to be the correct answer. The correct answer is A. So again, the complicated thing about here is just that it's been so long, right? The actual problem isn't so bad once you start refreshing yourself with this, but again, just been a while. Any questions or things that you'd like to add, Alec?
Nope, that was a good explanation there. I just noticed on the chat here, somebody said I joined late. I want to make sure this lecture was recorded and will be uploaded to D2L. Yes.
Yep.
Oh, yep. Somebody else already answered. Yep, will be.
I noticed we have 3 more minutes. I think we can do one more question. The other one that was has the highest number of votes here is 17B, also has 5 votes on it. And so why don't we spend our last 3 minutes, we'll do this one. This one is really a chapter 6 style question, right? Because before Math 133, for instance, we didn't know what the derivative of the natural log is, and we didn't know what the derivative of exponents were, at least not at MSU, right? So I mean, certainly if you took your Calculus 1 class someplace else, they may have told you what those are, but that was new information for our MSU students, you know, transitioning from Math 132 to Math 133. And so we need to apply the derivative rules in order to come up with this, right? So, I mean, we have lots of derivatives as our answers. And in fact, I think the overall question up here for 17 says, yeah, find the derivative for each function. So I guess we could pause here and I could say, do I need to use logarithmic differentiation? AKA, do I need to actually impose my own logarithm into this problem? And this is a good review, right? How do we know when we need to impose a logarithm into the problem and use logarithmic differentiation rather than just using the rules that we know and love from Math 132 or Chapter 6? And so since we have a minute left, I'll tell you, we do not need logarithmic differentiation. Because notice, our only variable here, our only x, is in the exponent slot, and that's certainly fine. We need logarithmic differentiation anytime there's an x in both the base and in the variable, but in the base and in the exponent slot. But here with just the only variable here is in the exponent slot, we can get around this. We don't need to use logarithmic differentiation. So we're just gonna take it slow because there's lots of things, right? So this is gonna be the chain rule several times. Remember, whenever you use the chain rule, you work outside in. And so I'm looking here, the outermost function is that we're squaring stuff. And so when I go to take the derivative, we need to bring the 2 down, leave the inside alone, reduce our power by 1. So that's the first action that I do, is that I take the derivative of the outermost function. So the inside that I'm leaving alone at this point is the natural log of 2 to the x plus 1. Then we need to multiply by the derivative of the inside. And so when I say inside, I mean inside of the squaring function. So I'm looking now at what's inside of the squaring function. And I see there's yet another chain rule going on here, right? Another composition of functions, right? Now the outermost function is the natural log, and it has its own inside, right? 2 to the x plus 1. And so now, again, I'm working outside in. I take the derivative of the outermost function here, the derivative of the natural log now. So that's 1 over, leave the inside alone. So in this case, 2 to the x plus 1 is the inside for the natural log. Then I need to multiply by the derivative of its inside. So now I need to look at, right, taking the derivative of its inside, 2 to the x plus 1. And so the derivative of 2 to the x, remember for all these exponentials, you just get a copy of itself, and then you do the times the natural log of the base. And when you have e to the x, it's special, right? Because natural log of e is just 1. So that's why the derivative of e to the x is just itself. Plus, and when you take the derivative of 1, you would get 0. So you could write plus 0. You could just leave this out altogether. And this is going to be my final answer. We need to look and see, right, which of these does it actually match up with. So I noticed that I want my natural log of 2 to the x plus 1. So I noticed that A doesn't have that, for instance, and D doesn't have that. So, okay, between here, it looks like B or C. Notice that the natural log of 2 is what B is missing. So B is out. And if we check very carefully, it's nice that they even gave it to us in the same order. And if you work through this naturally, you get that the answer is C. Okay, so yeah, we're ended pretty darn close to on time. Again, I'm happy. I'll write out the solutions for these other ones that we didn't get a chance to talk over here in class. So if there was another one that you really wanted to see if you had the right answer or not, I'll upload those later today when I upload the video and whatnot to D2L. So again, that's going to be here under the videos section. So let me go back up to maybe the top here in D2L. Oops, it's frozen. Let me go ahead and refresh this and see if it snaps back. It was thinking about it, and then it came back to this. Oh, there we go. So yeah, it's under this videos tab up here. And then if you just scroll down to the bottom, we've done chapter 11, we've done chapter 8 and 10. I'm going to upload it here. The filled in class notes are where the kind of the ones that we weren't able to go over here in class are going to be. And of course, I'll upload the video and link it to here. I think that's all that I have. Anything that you want to add, Alec? And any last questions?
No, there's a question here that we'll go over after maybe you stop broadcasting. Somebody lost connection. We can go back and run that for you again in just a minute. Okay, but we'll hold off on that since everyone else saw it already.
Okay.
Other than that, I don't really have anything to add.
Okay, so why don't we go ahead and I'll stop the recording